Hello and welcome. This is a regenerative Rankine cycle, a fairly complex problem. As you can see, there is an open feedwater heater and steam is bled. Turbine is split into high pressure and low pressure turbine. And to make things more complicated, each of the turbine has a thermal isentropic efficiency of 88%. Same with isentropic, the pumps are also not isentropic. So that's why you have double states at the exit of the pump, double state at the exit of the turbine, etc. To simplify the problem, however, instead of selecting two different, individually analyzing each turbine, in which case we would have needed two more states here and here, what we have done is, what we are planning to do is that we will take these two turbines together as a system. Then we don't have to find those two states. Of course, they had thermodynamically the same state, but they will have different mass flow rate. To understand the TS diagram and the eventual solution we are going to present, it is very advisable that you print out this page or at least have this schematic in front of you. Then it will make more sense. I'm going to look at another computer where I have the schematic. That's how I can do the recording. Otherwise, there are so many states, it's very easy to get confused. So to see the TS diagram, I've already transcribed it here. There are three different pressures. There's a boiler pressure, bleeding pressure, and condenser pressure. And we'll keep this terminology in the solutions too. 1 to 2 is the isentropic turbine. 1 to 3 is the actual turbine. Just as 3 to 5 is the actual turbine. So really, the 1 kg per second is coming to turbine 1, flows through here. This is still 1 kg per second. Suppose we say the total flow rate is 1 kg per second, then a fraction of it we'll call F times that is bled from the turbine. So what comes here would be 1 minus F kg per second, or whatever is the flow rate here, F times that. So this reduced flow is passing through the condenser from 5 to 6. And again, the pumps are 6 to 8 is the isentropic actual pump, 9 to 11 is the actual pump. But after the first pump, from state 8, as you can see, the liquid goes to the feed water, just as the bled steam from state 3 is coming from the turbine, goes to the feed water. And the feed water heater, they go to the feed water heater. And the condition of the bleeding is that the exit state 9 must be saturated liquid. You have to, that gives us the clue of how to find F. So in other words, if we do an energy balance on the feed water heater, then we can see that we will get an equation something like H9 must be equals, which is the exit to the feed water is 1 minus F times H8. That's what is coming here, and F times H3, and that will give us an equation for the feed water. In other words, to find F. So everything else is kind of straightforward. So let's go and set up the given parameter first. I've already done so. I'm just going to walk you over. So as you can see, the boiler pressure in kPa, the maximum temperature in Kelvin, bleeding pressure in kPa, condenser pressure in kPa are all listed here. These are given information. So are the turbine efficiency and the pump efficiency in fractions. And this is the F, the fraction of steam that must be bled. The equation that I just presented in the PowerPoint, I simplified that, and this is the equation that basically, obeys the energy balance and produces the fraction of steam that must be bled from the turbine. As far as calculating the states are concerned, again, these are pretty straightforward. For state 1, which is the inlet state to the first turbine where all the analysis begins, P1 is known, T1 is known. Again, see how am I using the variables. And I'm just assuming m dot to be 1 because in this particular problem m dot is not given and the basis is 1 kg per second to the boiler. So we have to find the fraction of that is bled from the turbine. Of course, the problem can be scaled up by changing m dot to any value and just doing a super calculate later. Okay, So if we now go to state 2, which is an isentropic exit state, we know it's a the pressure would be the bleeding pressure, and entropy is equal. But look at the mass flow rate. M dot 2 is F times M dot 1. And why we could not, this white background means M dot 2 is unknown. That's because if you go there, F could not be calculated this time because we don't know these states, H9 and H8, etc. So therefore, but once F is known, all the other states are known, a super calculator will enable us to calculate M dot 2. Okay, so let's leave it at unknown. State 3 is the actual state, which is, so we know the bleeding pressure, but H3 is, again, we use the turbine efficiency in this formulation. So it's the, just to show you the equation I used here, it's a standard isentropic, actual versus isentropic turbine comparison, and that produces what is the unknown H3. State 4 is the isentropic exit pressure exit state for the low pressure turbine, and so the pressure is the pressure of condenser. And if you look at the schematic, you can immediately recognize that. And again, I'm putting state 4, mass flow rate would be M dot 1 minus M dot 1 times F. In other words, it's a difference in mass flow rate that flows through state 4 and through the condenser, etc. State 5 is again the actual exit state. So I'm again, the equation is not actually you can see the equation I'm using right here, by the way. If I just put the pointer over H5, then you will see that the equation I'm using for H5 appears there. So on mouse over on H5, you can see that I'm using the turbine efficiency to find H5. State 6 is again the condenser exit, so therefore the quality of steam is going to be 0. Saturated liquid, pressure is condenser pressure. Again, the mass flow rate is the same as the difference between the total mass flow rate and the bled mass flow rate. State 7 is isentropic pump exit state. So pressure has been increased to P bleeding by the first pump. That's why we need 2 pumps here. One pump is to raise the pressure to the bleeding pressure. Otherwise, we cannot mix the 2 fluid. State 9, state 8 and 7 must have the same pressure as state 3 and 2. And this is the feedwater heater is nothing but a mixing chamber, and the pressures must be equal. So that tells us that the first pump exit pressure is P bleeding, and we know the mass flow rate in the same, must be the same as what passes to the condenser, and it's isentropic. But the actual exit state, of course, will need, again, you can see the formula used for H8, which involves the pump efficiency and known parameter. This way it can be calculated. For state 9, which is the open feedwater exit, now the only condition is that the quality must be 0. And of course the mass flow rate will become same as M dot 1, the whatever flows through the boiler. So state 10 is the second pump, because the exit, the flow from the feedwater heater must be raised, the pressure must be raised to the boiler pressure. That's what we are doing. The P10 equals P boiler, and of course mass flow rate becomes M dot 1, and it's isentropic. This is the isentropic exit condition. This is needed to find the actual exit of the pump. So again, we are using the pump efficiency, as you can see in this space, to calculate H11. Now that all the states have been calculated, you can make a check on them on the graphics panel and draw a constant pressure line, for instance, through different states. This would be the bleeding pressure. Well, all the state numbers don't show up because of the zoom levels. If you just can select a part of that plot, and you can see that the state number will show up as you zoom into a particular part. Anyways, But this should be done as you calculate state after state to make sure each state is correct. In the device panel, we can set up all devices. Device 1 is our turbine. It's a multi-mixing device, as you can see, because we can choose the type of device here. There are one inlet and there are two exits for this turbine. Heat transfer being 0, work is calculated. So that's quite simple. Device 2 is the condenser, I believe. Yes, 5 to 6 is the condenser. So heat transfer is calculated. There is no work transfer. Device 3 is 6 to 8 is the first pump. Pump work is calculated here. Again, it's a single flow device. Device 4 is the feedwater heater. So this is another multi-mixing device. But here, this time there are two inlets and one exit. And of course, work transfer is 0 in a mixing chamber. And Q dot is calculated to be 0. That kind of checks on the integrity of our calculations, because we use this assumption that the feedwater heater is adiabatic to find the bleeding rate F, if you recall. The next device, the device 5 and 6, there are two more devices only. This is the second pump, and which has a 5, 9, and 11 are the inlet and exit states, and work is calculated. And finally, device 6 is essentially the boiler. We're going from 11 to 1, so heat transfer is found. So as long as your devices make a loop, in other words, they're exactly same inlets and exit. If you think about it, each number should appear as either an inlet and exit. So state 5, suppose it's inlet to a device, so it must be exit to another device. So anyway, so it uses this counting technique to make sure the cycle is complete. Otherwise, you will not see any output here. And the first thing to check in a cycle is that W.net must be equal to Q.net. Otherwise, something is big time wrong. Thermal efficiency is calculated. So imagine now it's how easy it is to evaluate effect of any parameter. The way we set up the problem, we could just go here, isolate user variables, and we can just we say what would happen if the bleeding pressure were not 700 kPa, but let's say we say 2000 kPa. We just increase the bleeding pressure. We calculate this, and before you super calculate, let's make sure you remember the efficiency is 39.43. Now if you super calculate, come back, look, the efficiency has decreased. So it's very easy to do a parametric study, for instance, to find what is the optimal bleeding pressure that will produce the highest thermal efficiency.